Okay, this is topic 6.3, part 2, and this is the second fundamental theorem of calculus. So we could say that this is FTOC2. Now I'm going to tell you right now, if there was ever something that was simple, it's the FTOC2. What I would like to do, and please let me know if you would like to see all of this guides you into a proof of it. Okay? What I would like to do right now is omit this. I know you're probably shocked. You've never seen me do that. And let's go straight to FTOC2, which is what we said. FTOC2. Now, it is very straightforward, and so I'm just going to define this just like this. And here we go. The second fundamental theorem of calculus says that if someone gives you a function and that function is equal to an integral. Now that's pretty powerful. Someone gives you a function and that function is an integral. The derivative of that function that was given to you as an integral is just equal to f of x. Now, it's going to be a little crazy. The upper limit of integration is x. If you have the lower limit of integration as a constant, and I mean any constant, lower limit, and it has to be the lower limit of integration must be a constant, and that's any constant, in order to use this FTOC2. So is a constant? Yes. So once that's a constant, you just take this x and plug it into f, and that's equal to f of x. I'm not joking. Now, what happens if the upper limit of integration isn't just x? The derivative of x is 1. So technically, you could say multiplied by the derivative of that upper limit of integration, it would be 1. Okay? So what if we have some function of x here instead of just x? Well, guess what? Now, the derivative of capital F of x is equal to f of g of x. So you're going to put all of that function into f multiplied by the derivative of g. Okay, let's jump right in and learn while we're working. Okay, in number 1, f of x is, and it could be called anything. Somebody could give you g of x. Don't let capital F of x bother you, okay? So someone gives you a function, and that function is an integral in this case, and that's your indicator that you're using FTOC2. There is no integration in FTOC2, no integration methods, okay? So what do we have to do? Is the lower limit of integration a constant? Yes. The upper limit of integration is just x, so we're in great shape. So when we take the derivative of f, all we do is plug an x in everywhere there's a t. That's it. I know that may seem a little bit silly, but that's it. And the FTOC2 is used, I will tell you that there is an optical physicist. Hope I'm spelling that right. Well, maybe I won't. An optician. And many of these optical studies uses lenses. They use lenses. They study eyeglass lens, and they use FTOC2. I'll be showing you one of those. Okay, so don't think it's just a game here. This is serious. Lower limit of integration is a constant. They've given us a function that's equal to an integral. The upper limit of integration is a function of x, so we will have to use the chain rule here. Let's give it a try. The derivative of that function that's equal to an integral is equal to the sine of x cubed multiplied by 3x squared. Now, we should leave this in a nice form. 3x squared sine of x cubed. Okay? Let's try number 3. Okay, lower limit of integration is a constant. I wish I would have switched these up. Upper limit of integration is a function of x. So now, when we take the derivative of that function, we just take that 4x and we put it in h of t. So now we have h of 4x, and then multiply by the derivative of 4x, which is 4. So we have 4h of 4x. 4 times h of 4x. Okay. What's up with number 4? You guessed it. I don't see a constant as my lower limit of integration. So what I'd like you to do is pretend like you have this number line and you're going from negative x to positive x. Now, x could be a negative number, and these could be switched, okay? If x was negative 5, then the opposite of negative 5 would be over here. But just for drill, I just want you to know that 0 is between the opposite of a number and that number itself. So we're going to break this up, okay? We could integrate from negative x to 0 and 0 to x. Let's do it, okay? So we're first, before we use the FTOC, we have to rewrite capital F of x as the integral from negative x to 0 of 5t dt, and we're going to add that from the integral from 0 to x of 5t dt. Now, we can apply FTOC2 to this one because the lower limit of integration is 0. But how about on this first integral? It is not. So we need to rewrite this as the integral, as the opposite of the integral from 0 to negative x of 5t dt plus the integral from 0 to x of 5t dt. Now, let's look at our lower limits of integration. They are both constants. So now we can go ahead and use FTOC2. Let's go ahead and put that negative there, and we're going to take 5 times a negative x. And the derivative of negative x is negative 1. Plus, lower limit is a constant. Upper limit is just x. So we don't have to use the chain rule, and we get 5x. So let's go ahead and simplify that a little bit. And we now get 5x, multiplied by negative 1. So we get a negative 5x plus 5x, and we get 0. Okay? And let's look at our next problem. Again, let's just picture a number line going from 2x to 3x and putting 0 in the middle. And again, guess what? 3x could be on the other side if x was a negative number. And we're going to add these two integrals together. So we're going to rewrite f of x as the integral from 2x to 0 of t squared minus t dt. And now we're going to add that from 0 to 3x of t squared minus t dt. We are set up already for this second integral. But this first integral, we need to change the lower limit of integration. So it's the opposite of the integral from 0 to 2x. We are set up for FTOC2. And you know what I just saw over here? I just saw that I never wrote that now I'm getting ready to plug these values in. So right here, this was the derivative. Okay? we're taking the derivative of these functions that are integrals. So really, you know what you're doing? You're taking the derivative of an integral. So let's go. F prime of x is equal to, I need to grab that negative while it's there. Again, let's check our lower limits of integration, our constants. Here are our upper limits of integration. So now we're going to go ahead and plug 2x in. So it's 2x all squared minus 2x. And then we have to multiply all of that by a 2, because that's the derivative of 2x. Plus, now I'm going to plug a 3x. And then I have to multiply all of that by a 3. Not a problem. Let's take our time so we don't make an error. And I end up with the opposite of 4x squared minus 2x, all times 2. And why don't I put that 2 in the front? A negative 2. And then I'm going to go ahead and add 3 times 9x squared minus 3x, negative 8x squared. Goodness. Negative 8x squared plus 4x plus 27x squared minus 9x. Okay, so it looks like I can combine my x squared terms and I can combine my x terms. Okay, so 27 minus 8 is 19. And then a 4 and a positive 9, a 4 and a negative 9 leaves me with minus 5x. So that was quite a problem. I don't think you'll see any that difficult, but maybe not so difficult. Definitely using the properties of integrals with these, because with FTOC2 we need the lower limit of integration to be a constant. And that concludes part 2 of